In the last lesson, we were talking about FIR, finite impulse response filter design by windowing, right? And we actually did some examples um, using different kinds of windows, right? Different kinds of time windows. I mean, so the one thing that we uh, left out was about the design of bandpass and high-pass filters. So in the previous examples, we were just dealing with low-pass filters. A low-pass filter is basically just a boxcar that's kind of centered around zero frequency, and the boxcar has a boundary which is minus omega c to positive omega c. That's your corner frequency of your low pass filter, right? And at the beginning of this lesson, I was sort of telling you that once you know how to construct low pass filters, you know how to construct high pass and band pass filters, right? So all you have to do is to actually shift your low pass filters, right? And that's indeed the case. Actually, that's indeed the case. So let's just look at how you can actually construct a bandpass or high pass filter just by shifting those low pass filters. So here it's a low pass filter, right? This is the time domain representation, small h LP low pass, right? And then this is the frequency domain representation. Time domain representation is just a function of time, which is indexed by n, and then frequency domain representation is a function of omega frequency, right? And for the ideal boxcar in the frequency domain, that's exactly 1 between this band and exactly 0 everywhere else, right? And that's our low pass filter. So if we wanna shift this low pass filter, how are we gonna shift it, right? So if we want to do a band pass filter, what we would like to have in the frequency domain is something like that, right? For band pass filter, if you go back to look at the figures, it's basically this boxcar, right? And that you shift this boxcar to the positive frequency side to get this boxcar, right? Suppose this boxcar is centered around some frequency that's, say, omega 0, for example, right? And then you also want to shift this boxcar to the negative frequency side, right? And then this boxcar is sort of centered around minus omega 0, right? Minus omega 0. So what you want to do is to have two boxcars basically. One is the one that's being shifted to the positive frequency side. So this is the low pass boxcar that's being shifted to the right, right? So for this particular boxcar, it's centered around positive omega 0, right? So you can sort of see it's omega subtract omega 0, right? And then for this boxcar, it's centered exactly around minus omega 0, right? So your bandpass filter is gonna look like that. So what you need is to shift this boxcar to the positive side by omega 0, and also shift it to the negative side by minus negative frequency side by omega 0 also, and then add them together. Then you get your bandpass filter, right? So all we have to do is to do this kind of shifting in the frequency domain. But what's gonna happen if you do this kind of shifting in the frequency domain, and what's gonna happen in the time domain, right? Here for the low pass filter, you have a time domain representation. That's this h, right? For this boxcar, the time domain representation is just a sinc function, right? It's a sinc function. So if you actually do this kind of shifting, both to the positive side and to the negative side, and then add them together, then what's going to happen in the time domain, right? What's going to happen to the time domain representation? So to do the calculations, we need to use the frequency shifting property of the discrete Fourier transform. It is one of the Fourier transform properties that we talked about in lesson 3, right? Just the previous lesson. If you guys don't exactly remember what this property actually is, I can sort of find out the slide for doing the proof of this particular property. It basically tells you that if you are doing a shifting in the frequency domain to the right by omega 0, right? To the right by omega 0, that's a shifting to the right by omega 0. Then in the time domain, what you have to do is to multiply the original time sequence with the complex exponential e to the j omega 0 n, right? And you can imagine what's going to happen if you shift it to the left, right? If you shift it to the left, it's omega plus omega 0, but in the time domain, it's going to be xn times e to the minus j omega 0 n, right? So that's what we have to do. All we have to do is to multiply the time domain representation with e to the j omega 0. Omega 0 n, omega 0 is sort of the amount of shift in the frequency domain. So for this particular representation, for big H AOP e to the j omega j subtract omega 0, its time domain representation is going to be small h AOP times n, small h AOP n times what? Times e to the j omega 0 n, right? And then for this particular boxcar, which has been shifted by minus omega 0, it's shifted to the left, right? And then the time domain representation is going to be small h AOP n multiplied with e to the minus j omega 0 n, right? And then all you have to do is to add them together, right? Small h AOP, that's the xn here. The small h AOP is going to be the same for these two terms, right? You can take it out. And then what you have to add together is e to the j omega 0 n plus e to the minus j omega 0 n, right? And from Euler's equation that we know, these two exponentials adding together actually equals to 2 times cosine omega 0 n, right? So in order to actually get a bandpass filter from a low-pass filter, all you have to do is to multiply h AOP n, the low-pass filter, the time domain representation of the low-pass filter, with 2 times cosine omega 0 n, and that's it. And then and omega 0 is what? Omega 0 is the center frequency of your bandpass filter. That's the location of this boxcar, basically, omega 0, right? That's the center location of this particular boxcar, right? It's center omega 0. That's your bandpass center frequency, right? And then minus omega 0 is here, right? So that's how you can actually get a bandpass filter from a low-pass filter. So all you have to do is to multiply 2 times cosine omega 0 n, right? But what about high pass, right? If you know how to do bandpass, then you know how to do high pass, right? High pass is just shifting more. All you have to do is to shift more, but you have to account for something that's not exactly the same as bandpass, right? So you have to duplicate the boxcar here, right? And then you have to duplicate the boxcar here, right? But minus pi and pi, the interval is exactly 2 pi, basically, right? So if you do the same thing as the bandpass, you shift by omega 0, right? Omega 0, but now omega 0 has to be pi. You have to shift them by pi, you see? So so this boxcar is duplicated here, right? But if you duplicate this boxcar here, don't forget the whole boxcar train actually has a fundamental period of 2 pi, right? So if you have another boxcar here, these two boxcar duplicate, repeating itself by 2 pi. Then for this boxcar, the next cycle is going to be right here, right? The next period is going to start. For this boxcar, it's a repetition. On the positive side, it's going to be right here. That's the next one. And then you still have another one that's at the 3 pi, right? And then for this boxcar, its duplication, or its a cycle, its next cycle on the negative frequency side is exactly right here. Do you see? So if you actually repeat the same kind of calculation here, then you're gonna have 2 boxcars located at the same location, right? And to account for that effect, all you have to do is to divide by 2, right? Get rid of this 2, then you get your high pass filter, right? If you don't exactly maybe I didn't explain this thing very clearly. What I'm saying is basically for bandpass, you are basically duplicating this boxcar here, right? But for high pass, you have to duplicate your boxcar here and here, right? But don't forget the whole thing. The whole boxcar train has a fundamental period of 2 pi. right? It has fundamental period of 2 pi. So for this boxcar and this boxcar, these two boxcars are going to repeat itself with a period of 2 pi, right? And then for the next repetition, this boxcar is going to be shifted to is going to be replicated here, right? So effectively, you're actually having two boxcars at the same location for high pass, right? Because for high pass, it's centered around the boxcar is centered around minus pi and pi, and the interval between them is the exactly 2 pi. So in order to account for that, you're having two boxcars at the same location, you have to divide this thing by 2. Divide this expression by 2. Right, divide this expression by 2. So in order to actually get a high pass filter, all you have to do is to multiply the low pass filter with cosine without the 2, and then you get your high pass, right? And then that's basically how you can actually do an FIR filter design by windowing, right? So let's try to do a summary. So the first thing you're gonna do is to select a suitable time window, a suitable windowing function, right? And this windowing function is going to be used to multiply with the time domain representation of your ideal response, right? What's going to be your ideal response, right? For now, all the examples that we have looked through, the ideal response is actually a frequency domain boxcar, right? For low pass filter, it's a boxcar centered around zero frequency, right? That's our frequency domain representation, right? And then this ideal representation actually has a infinite impulse representation in the time domain, an IIR representation in the time domain, which is basically the sinc function, right? A sinc function has infinite response, right? And then what you have to do is to basically multiply this suitable time window, selected time window, with that time domain representation of your ideal response, right? And then the result is going to be so the third step, compute the coefficients of the ideal filter, which is basically the time domain representation of big HD, right? We call it small HD here, right? And then all you have to do is to multiply the ideal coefficients by the windowing function that you have selected, right? And then what you can do is to evaluate the frequency response of the resulting filter, and then you can sort of look at them, right? Look at them if it is what you wanted, and then you're done. If it is not exactly what you wanted, then you have to iterate this whole process. Typically, what you want to do is to just increase m, which is the number of points, right? The number of points used for representing this HD, right? And then you can sort of make improvements to a filter and look at the look at the results of applying the filter that you are actually just constructed. So that's how you can actually construct filters by doing this windowing of a time domain representation of a infinite impulse response, basically the sinc function, right? But now let's look at how we can apply those filters, right? How we can actually apply those filters on on some kind of signal, right? Let's try to use those filters, and I'll show you how you can use them, right? So now let's write some additional scripts, or just reuse S3, the third script, right? And we're just gonna add stuff to it. So let's try to construct a signal first, and then we're gonna apply our filters onto that signal, right? So let's try to construct a horizontal axis for this particular signal that goes from that's the horizontal axis of our signal that goes from like 0 to 1023. Then this is exactly 1024 points, right? And then let's try to construct our artificial signal. SC equals to 1 subtract 500 dot square divided by 4 and dot multiply exp minus x subtract 500 square divided by 2 divided by 4. Right? let's just execute this. Right. And then let's just make a plot of it. Maybe I should use stem. Right. So it is some kind of function that multiply with another exponential function, right? And we're going to use this function, use this particular signal as our input signal to the various different kinds of filters, and then we're going to see what's going to be the effect of this particular filter, right? And it looks like it's actually some kind of derivative of a Gaussian, right? Um, so that's exactly what it looks like. It looks like a derivative of the Gaussian, right? It's some kind of derivative of Gaussian. And so let's first try to filter it with a boxcar, right? With just an ideal filter, but it's a kind of an FIR filter that's designed using a boxcar time window. Basically, we have to sort of be careful about about the about the windowing function and also the low pass filter, right? So this ideal target frequency, target this ideal filter in the frequency domain is a boxcar, right? And in the time domain, it's a infinite impulse response. And then we're gonna, which is a sinc function basically. And then we're gonna window that sinc function using a time domain boxcar, right? And then we have to be careful about the boxcars, right? When we say boxcar, it could be in the time domain or could be in the frequency domain depending upon the context, right? So now let's try to construct this time domain FIR based on a boxcar time window, right? So n goes from -10 to 1 to 10, right? That's gonna be the horizontal axis of the filter, right? And then h, that's gonna be our time domain response of that um, of that filter, low pass filter. Right. So that's the horizontal axis of the filter, time domain representation of the filter, and then that's the sinc function. And because this is actually a finite interval, right? It goes from just -10 to +10. So this impulse response computed using this finite interval is going to be finite duration, right? It's not a sinc function that's oscillating forever. It only goes from -10 to +10. And this line is just to get rid of the not a number at the center of that sinc function, right? And then what we can do is to sort of apply this filter onto the input signal, right? And what we can do is how do we actually apply the filter, right? We can apply the filter by using a convolution operation, right? Because both of the input signal and the filter have been specified in the time domain, right? So if you wanna apply a filter to an input signal, you can do it in either way, either in frequency domain or in time domain, right? In frequency domain, it's just a multiplication, and we know from the Fourier properties, multiplication in the time domain is actually equivalent. Multiplication in the frequency domain is actually equivalent to convolution in the frequency domain. Convolution in the time domain. So all we have to do is to convolve this time domain's input signal with the time domain impulse response of our low-pass filter, right? So all we have to do is to do this. So y ny, that's going to be our output equals to conv underscore m. Conv underscore m is our own convolution routine, right? It's going to compute the horizontal axis of the output signal. So then our two inputs, right? That's the input signal and its horizontal axis, and then the filter. And the filter is going to have a horizontal axis that also goes from minus 10 to 10, right? And that's n, right? Let's just use this one, right? So then let's make a plot of it. We're going to do a subplot, and then plot ny and then xlim 400 to 600, for example, right? And then we're also going to plot the frequency domain representation of the filtered signal, right? And we can obtain the frequency domain representation of the filtered signal by just doing a FFT, right? So we're going to plot it in a separate window, a separate subplot. And then SF1 is going to be FFT of Y, right? And then we can just plot we need to construct the horizontal axis of the frequency, horizontal that's basically 0 to pi with this many points, right? Link space. I was using link space to construct the frequency axis, and then all I have to do is to plot the amplitude spectrum, basically SF1. And then let's plot it in red, right? So a better plot would be a plot that's comparing the filtered signal, time and frequency domain filtered signal, with the time and frequency domain unfiltered signal, right, before filtering. So subplot 211, but let's hold on to it. And then we also plot XS maybe, right? That's the time domain signal before the filtering, and then that's the time domain signal after filtering, right? And then what we have to do is to do the same thing for the frequency domain. So let's also hold on to the let's just SF equals to FFT of S, right? And then plot link space 0 to pi. In this case, the total number of points is 1024, right? So half of it is 1212, and then all I have to do is to plot ABS SF1 to, right? And then that's the frequency domain representation of the unfiltered signal, the original signal, right? Before the filtering, and then that's the filtered signal, right? So let's just run it. So here it's what it looks like, right? So before the filtering, it looks like the blue curve. See, the blue curve, right? And then after the filtering, it looks like the red curve. That's in the time domain. And then that's in the frequency domain, the amplitude spectrum. And you can sort of see ripples, right? And what exactly was our filter? Our filter is has a corner at about that's the corner, right? The corner here, it's about pi divided by 4, a quarter of pi. That's our corner frequency. So if you go back to look at the spectrum, right, a quarter of pi divided by 4, that's about 0.8. So 0.8 0.78 something. It's about here, right? So you're basically getting rid of all the high frequency content, right? So the red curve is the amplitude spectrum of the filtered signal. You can sort of see the effect of the low pass filtering. It has removed lots of the energy at high frequency, right? And another thing that you have to sort of pay attention to is that this filter is actually a zero phase filter, right? So when we constructed this H, the horizontal axis for it is from -10 to 10, right? It's completely symmetric. It's completely symmetric, right? So this H goes from -10 to +10, and when we did the convolution, the horizontal axis that's being used for H is exactly n, right? It's a symmetric time domain representation. So it has non-zero amplitudes at negative time, basically, right? In negative time. So it's actually a zero phase filter, and on the time domain filtered signal, you can actually see that. See. So before the filtering, the input signal is the blue curve, right? And after the filtering, the signal looks still at the same location. It's not being shifted anywhere, right? It's still symmetric at the original center, which is at about 500. It's not being shifted in either of the directions, right? This is the indication that the filter itself actually has zero phase, right? It's not really changing the shape. It's not really changing the location of the input signal, and it's not changing the shape either, right? It's still symmetric around 500. See, right? And that's a zero phase filter. But a zero phase filter is non-causal, right? Because you have to use future data points in order to actually compute the filtered signal, the output signal at the current data point, right? So it's a non-causal filter. It can be applied after you have recorded the complete sidewinder, right? You can do that. But for real-time applications, you probably don't have the luxury of using a non-causal filter, right? So in some cases, you might want to use a causal filter. So in order to actually convert it into a causal filter, it's actually quite simple. All we have to do is to shift the filter, right? All we have to do is to shift the filter by a certain amount. So next we are gonna do is to filter it with to filter the same signal by using a causal filter, right? All we have to do is to shift the horizontal axis of H, right? And we don't really have to sort of change this n. All we have to do is to change the input to the conv_m function, right? We change the horizontal axis here. So now let's do a y, ny now equals to conv_m, right? And still s, and then the horizontal axis of s, h. But now let's give it a different horizontal axis for the filter. Instead of from -10 to 10, we're gonna give it from 0 to 20. Sorry. Right, and then that's gonna be the filter that's filtered using a causal filter, right? And then we're still gonna make a plot the causal filter, the result of the causal filters. And then just plot ny, but with a different color maybe. Let's just use K. Use black, and then subplot xlim 400 600. Right. Then subplot 2 1 2 SF1 equals to FFT y, right? And then again plot. You can just copy this line here. But let's change the color from red to K. So for this particular filter, all we have changed is the phase of the filter, right? We're basically shifting the entire impulse response of the filter in time domain by 10 points basically, right? And the amplitude spectrum, the amplitude of the filter is not going to change, so it's not going to the output signal, the amplitude spectrum of the output signal is not going to change either. So let's just run through this particular segment. Right. So as expected, right? That's the amplitude spectrum. The black curve is right on top of the red curve, right? Amplitude spectrum is exactly the same. But in the time domain, the filter signal, that's the black curve. The filter signal has been shifted by a certain amount. It's no longer at the same location of the original unfiltered signal, the blue curve, right? It has been shifted to the right by a certain amount, right? But the advantage of this particular shifted filter, the filter that's actually producing the shift, is that it's actually causal. To compute the output signal, you don't really need future points. All you need is past points, right? All you need is past history points, history inputs, right? And then you can compute the output. And you can sort of see the shape of the output is actually the same as the shape of this zero phase output, right? The black curve and the red curve, the shape are identical. The only difference is that it has been shifted by a certain constant amount. And that's sort of the benefit of using a linear phase filter, right? A linear phase filter will just produce a shift in the time domain, right? And it's not going to change the shape. It's not going to distort the shape of the waveform. See, and that's a good feature, right? And you have made the filter actually causal. So that's a good thing, right? So that's filtering. That's filtering by using an FIR filter constructed using just a time domain boxcar, right? The time domain window for that particular FIR filter is actually a time domain boxcar. Now let's try to use a different time domain window. We're gonna use a Kaiser window, right? So we're gonna construct HW equals to H dot multiply Kaiser. How many points we have? We have 21 points, right? And then the order of the window. We looked at the effect of having a that's basically the beta value, right? That's basically the beta value. If beta value is very large, then it's gonna be very smooth. The window constructed is gonna be very smooth. So here we're gonna give it a non-zero beta value. That's 5. Let's give it 5. So you can adjust this value based on the output signal. Is it what you want it, right? If it's not exactly what you want it, you can adjust this parameter to redesign the filter, right? And then all we have to do is to apply this filter, right? So y equals to CMV underscore m s n x, right? And then instead of using h, we're gonna use hw. That's gonna be our filter, right? And then the horizontal axis, still we want a linear phase filter. We want a causal linear phase filter. So the horizontal axis is still gonna be 0 to 20, right? So just to make it a causal, right? And then let's still make a subplot 2 1 1, and then plot ny y. This time let's use a green color, right? And then subplot 2 1 2, right? SF1 is gonna be FFT y, right? And then I'm just gonna copy this very long line. And again, we're gonna use green. Also use green. Right. This time the amplitude spectrum is gonna be different because the filter is different in the frequency domain. And let's just run through this block. Oh, looks like I got something wrong. So if I do the size of H, it's telling me 1 by 21, right? But if I do the size of Kaiser 21.5, it's telling me it's 21.1. So you cannot really do a dot multiply. You have to sort of transpose it before doing the dot multiply. And then you can just run it, right? And then That's our green curve, basically, right? That's green curve. So again, it's causal. So in the time domain, you can sort of see you have a constant phase shift, but the shape is still symmetric, right? And if you want to sort of see some more details, you can blow up this segment, right? The reason it's different from the black curve is because the filter is different, and you can sort of see that from the frequent domain representation, right? And you can sort of see less ripples, less amount of ripples, right? But the transition band is like wider, right? That's one of the trade-offs that you have to make, right? If you want smaller ripples, then your transition band is still gonna is likely going to be wider, right? So it transitions from like a large amplitude to like a very small amplitude in like a longer distance in the frequency domain. So that's sort of the effect of changing the time domain window from a boxcar to a Kaiser, a smoother window. Now let's try to write a function. Let's try to write a Matlab function that's gonna implement the whole procedure, right? And we're gonna define some kind of input and outputs for this particular function. This function is just gonna be called FIR. Right. Matlab has its own FIR functions, right? But this is something that we can sort of write by ourselves, not without too much of a difficulty, right? So let's just by writing this particular function, we can understand better what we have to do in order to design a FIR filter, right? So it's gonna take a bunch of inputs, big N, which is basically the number of points of that. So here we are using how many points for these examples? That's the input signal, right? That's the input signal. And then for the filter, we're actually using 21 points, right? So we need to sort of specify how many points we want to use. That's basically the order of that FIR filter, right? How many points you want to use for that particular time domain representation of the filter. And then WC is omega C, basically, the corner frequency. WO is omega 0, basically. That's the center frequency. And then WIND is the window type. And then we can sort of have a bunch of choices for those different types of windows. 1 is rectangular. Henning is a Henning window. 2 is a Henning window. 3 is a Hamming window. And 4 is a Kaiser window. Right. And then the output is just going to be the filter itself. The filter itself. And then B is just like in S3, in the script, it's either H or HW, basically. That's B. And you can use B. You can use B to filter an input signal by just doing a C1V underscore M. Right. And you can control whether the filter is a zero phase or a causal filter by just specifying the range of the filter. Here we're actually specifying the range to be causal, right? It goes from like 0 to 20. So if you don't want to use a causal filter, you want exactly a zero phase filter, then what you can do is to give it a different horizontal axis when you do the C1V underscore M, right? Here it's N goes from -10 to 10, so it's a non-causal filter but has zero phase, right? And then the reason that we have both WC and WO is because we're gonna construct both bandpass and high-pass filters in this particular function also, depending upon what's actually the value for WC and WO, right? So WC is the corner, but WO is going to be the center frequency, right? Normalized. All of them are normalized. So WC and WO is going to be the expected value is going to be between 0 and 1, including 0 and 1, right? So if WO is 0, then we're actually constructing a low-pass filter. And if WO is 1, then we're constructing a high-pass filter. And if it's a value between 0 and 1, then we're constructing a bandpass, right? WC basically specifies the width of the filter, right? It's a corner. The corner is basically the width of the filter, right? For a low-pass filter, that's the width of the low-pass filter. But if it's a bandpass filter, that's going to be half of the width of the entire bandpass filter, right? So let's look at how this function is written. So we need to construct a horizontal axis for the filter. N goes from 0 to big N. Big N is the number of points that we are actually specifying. So the number of points for the filter is actually big N plus 1, right? big N plus 1, the number of points. The order is called is big N. It's called the order. And then depending upon the window parameter that I actually specify, the user is actually specifying, you can construct the windows, right? So it's basically constructing windows. Boxcar, big N plus 1, Henning, big N plus 1, Hamming, big N plus 1. And then Kaiser, big N plus 1, right? But here it's a 4.55, right? It's some number that I put there to just for testing purposes, right? But it doesn't have to be, right? Depending upon big N, you can actually specify a beta value depending upon the big N, or you can actually specify one additional input, right? That's the parameter for the window, right? For those windowing functions that doesn't take a second parameter, you just ignore that input parameter. But if for window function like a Kaiser that actually accounts for or takes a second input, you can use that input, right? And you allow the user to determine what's going to be that particular parameter you're going to use, right? And that's the time window that you're gonna construct, and the time window is gonna be stored in a parameter that's called window. That's it, right? And depending upon the input parameter wind, the stuff that's stored in window is gonna be different depending upon the window type. And then what you have to do is to compute the target response, right? The time domain representation of the ideal filter, right? And in this case, we are still using a boxcar, so it's going to be a sinc function, right? So here it's the numerator, and then here is the denominator, right? So basically, for either the numerator or denominator, the horizontal axis has been shifted, you see. So basically, we are actually constructing the default behavior in this particular function is actually constructing a causal filter. So the center of the sinc function, the peak of the sinc function is going to be centered at big N divided by 2, right? But in any case, you don't really have the output, the output of the filter doesn't really have a horizontal axis associated with it, right? So you can use B in either the zero phase case, which has to be a symmetric time axis, and it has non-zero amplitudes at negative time, right? You can use a horizontal axis with that kind of a non-causal horizontal axis with B, or you can use a causal horizontal axis with B. It doesn't really matter, right? But here, when you compute the sinc function, it's basically computing it, assuming that the peak is at big N divided by 2, half of the number of points, right? And then if big N is even, then at the center point you're gonna have 0 divided by 0, so you have to fix that. Right here, it's actually this piece of code is just fixing that point, that not a number point, and then that's B is gonna be that's the output basically. That's the output, right? That's the output. By assuming if it's a low-pass filter, then that's your output. Numerator divided by denominator times time window, right? The time window, right? If it's a low-pass filter, then you're done. That's your output, right? But if it's a bandpass or a high-pass filter, then you're not done yet. You have to do this kind of shifting. You have to multiply this thing, right? Multiply this thing. So in this case, you have to determine if it is a low-pass or high-pass or a bandpass, right? Based on WO. So here it's branching statements. So if WO is larger than 0, smaller than 1, it's some value that's between 0 and 1, then you do this thing. You multiply 2 times cosine omega 0 n, right? And then the 2, right? Divided by big H1. Big H was constructed by using FREQZ, right? So it's basically constructing a frequency domain representation of that low-pass filter that we just constructed in the time domain, right? And H1 is sort of the first point. That's like the zero frequency, right? The zero frequency amplitude of that filter. So if you divide it by 1, then it's at zero frequency, then the filter is going to have exactly the amplitude of the field of at zero. The amplitude of the filter at zero frequency is going to be exactly 1. So right, it's just a normalization. Right? It's not really essential, but it might be useful. Right? If otherwise, if it's a 0, then it's a low-pass filter. Then you just divide it by some kind of normalization filter. And if it's not, else if If it's equals to 1, then it's a high pass filter. And high pass filter, you just multiply cosine without the 2, right? And basically that's how this function is written, right? Now let's look at how to use it, right? We're gonna use this particular function to construct a high pass filter, right? Let's try to construct high pass filter using this particular function. I'm gonna use the order of the filter. The number of points is gonna be 14. WC equals to 0.2, right? That's the width of the filter, and WO equals to 1. So once WO equals to 1, we know it's gonna be a high pass filter, right? So it's gonna be a high pass filter. WO equals to 1, it's gonna be a high pass filter, right? So and then the window type is gonna be 4, so it's gonna be a Kaiser window. Oh, sorry, click on the wrong button. Right. If window type is 4, then it's Kaiser window. So that's sort of all the parameters that's needed for the FIR function. Then we can just do B. That's our output signal output filter, right? Equals to FIR. Pick M, WC, WO, and then wind. Right. And then if we want to look at the frequency domain representation of this filter, what we have to do is to use H F FREQZ, right? B1, right? And then how many points do we want to use to represent it? Let's use 256, right? So that's the same kind of technique that we used to look at the FREQZ function, right? The FREQZ function allows us to look at the frequency representation of a time domain, frequency domain representation of a filter that's defining the time domain. So B, that's it's a time domain representation, right? And then let's make another figure, and then let's look at what this filter actually looks like. Right, that's the time domain representation of this particular filter. And then this time we're gonna plot the amplitude spectrum of the filter. The absolute value of H, basically. But how do I enter the absolute value? Two, two, three. But this time I'm gonna plot the dB log 10. I think I missed the bracket, I think. And Y label is dB, I think. Right. And we're gonna plot the phase of H. I have to unwrap the angle of H. Right. Although the backslashes in the labels are just for latex outputs. Latex output. It's gonna print Greek letters, But on Matlab, on this version of Matlab I'm using right now, it's probably not going to work. But in your case, it should work if you have the latex interpreter that's kind of installed together with Matlab. Right. So let's just execute this block. So that's our filter, right? That's our high pass filter. You can sort of see it's it's time domain representation that goes from like we have 15 points, right? It's a 14th order filter, so we're supposed to have like 15 points. So here you can count it. There's 15 sticks here, right? Um, that's the time domain representation, and then that's the absolute value of the frequency domain representation. Absolute value of the frequency domain representation of the filter, and you can sort of see it's actually centered at one, right? Centered at 1. And you can sort of see the shape, right? It's actually suppressing zero frequency and enhancing high frequency, right? So 1, the horizontal axis is actually frequency normalized by pi. So 1 actually corresponds to pi. So if you actually compare this particular figure with our diagram for a high pass filter, that's a boxcar centered around pi, right? Because the FREQZ function only constructs like the positive frequency, so the negative frequency is not plotted. It's not plotted. You see, it's not plotted, right? But you can imagine on the negative frequency side, it's still gonna have you're still gonna have a boxcar, right? And because it's symmetric. So what you are actually expecting is you also have something that's going down there, right? That's the other half of the filter. And then that's plotting it in the linear scale. If you actually plot the vertical axis in the log scale, that's in terms of dB, then you can sort of see it's the passband, right? Corner frequency is like 0.2, so at 0.8 your amplitude has decreased to like a certain percentage of the unity, right? And then that's the side lobes, right? The oscillations, that's the ripples, and then that's the phase, unwrapped phase. So this function basically summarizes, this FIR function basically summarizes what we have talked about so far, how to design FIR filter, either with zero phase or with causal linear phase, right? And how we can actually try out different kinds of time windows and what's actually the effect of those time windows on the design FIR filter. And we also looked at how to apply those filters to filter some input signals, right? By using COMV underscore M, this particular function, right? And this particular function takes into account the horizontal axis. So by specifying the horizontal axis, you can actually specify what's going to be the phase of the filter. Right? Is it going to be zero phase or is it going to be a causal linear phase? Right? You can determine that by when you are actually calling the COMV underscore M function, right? And this thing minus 10 to 10 is actually zero phase but non-causal filter.